Hi friends, in this class we will discuss the linear transformations. Linear transformation uh, is again nothing but a transformation which is linear transformation. That is a linear transformation. Actually, it is defined in two vector spaces. Let us take two vector spaces V and W. And the linear transformation which is represented by capital T is defined on these two vector spaces V and W, and it is a rule. Okay, a linear transformation, actually it is a rule that assigns to each vector x in V. We are considering an arbitrary vector, so you should now onwards you should I hope that you should understand what I mean by a vector. Okay, an arbitrary vector, how it will be in your imagination, so that you should keep in your mind. So this linear transformation is a rule that assigns to each vector x, an arbitrary vector x, each vector. Okay, each vector, I'm representing each vector in V x, an arbitrary vector I am taking, a representative vector I am taking x. So it the base assigns to this vector x, and it will be a unique vector, another unique vector, and that is represented as t of x. Transformation of x you can call it, or you can read it like t of x transformation of x. So it is a unique vector t of x in W, our second vector space W, such that it should satisfy the two axioms, that is t of u plus v equal to t of u plus t of v. This is nothing but your additive property. That is a linear means linear property means additivity plus homogeneity. So for example, in your beta class you have studied superposition principle. So in order to satisfy superposition principle, additive property as well as homogeneous property should satisfy. So those are the necessary conditions. So in the same manner, here linear means a transformation is said to be linear, which should satisfy these two axioms. That is additivity property t of u plus v, where u and v are in u t of u plus v is equal to t of u plus t of v. This is additivity property, and we have homogeneous property like t of c into u equal to c into t of u, homogeneity principle. Yes, for all u v in v, and in v, and here also for all u in v. That means u and v are vectors in vector space V. Now actually yes, moving on to the next slide. For example, transformation Okay, now we are going to study kernel and range of a transformation. Kernel and range of a transformation. The kernel or null space of a transformation T is the set of all u in V such that T of u equal to 0, that is 0 vector in W. The kernel or null space of a matrix we have studied. Now the kernel which can also be equate to the null space you have already studied. How you can equate that we will discuss. First of all, you should understand what you mean by the kernel, okay, or null space of a transformation. It is defined for a transformation T. It is a set of all vectors, set of all vectors u in V. V means we know that V, W, and a transformation is defined T. Then V is known as domain, and W is known as its range. Okay, so this U is in V, such that this arbitrary vector U, when acted upon the transformation T of U must be equal to 0. That is 0 vector in W. That means it is a set of all vectors in the domain V, in the vector space V, such that it will map when the transformation is acted, then it will acted upon these vectors in V, then it will map those vectors, okay, those vectors into the 0 vector of W, that is range. You can visualize this. This is graphical representation. That is, suppose we have kernel like this. Kernel, it is a for example, consider a vector space V W V. A vector space V is R2. R2 means it is a set of all ordinates or ordered pairs. Set of all ordered pairs means you can imagine it like a plane. Now I am I'm taking some arbitrary vectors u in V. That means u is again an ordered pair. So u is points like this. Okay, u is a points like this, and it also includes the 0 vector also. So when this transformation T is acted upon these vectors, these points, okay, then it will map into the 0 vector in W plane. So such kind of vectors, set of all u vectors, is known as kernel. Hope you understood. Then the range of T. Now we are going to define the range of transformation T is the, yes, we have already said that, okay, the range of T is the set of all vectors W of the form T of X for some X in V. So range is for all corresponding points in this V plane. When acted upon the transformation, we will get a corresponding points in this W, and those corresponding points are known as the range of the transformation. Now, if T happens to arise as a matrix transformation, like T of X, transformation of X is defined as AX. Transformation of X is defined as AX, some matrix A into the vector in V, AX for some matrix A, okay, then the kernel and range of T are just the null space and the column space of A. Yes, that means we have some matrix A of order m by n, Okay, if you imagine, you will get it very easily. A, and the transformation is defined as a into x, where x is a vector in our domain. Then, according to our kernel definition, it is it is the setup for x in v such that t of x equal to 0. That means ax equal to 0. Ax equal to 0. That means ax equal to 0 set of all x means it is nothing but your null space. Then the column space. Column space means yes, column space means we have the column space of a matrix A is span of A1, A2, A3, etc. AN. That means span of columns of A. Span of columns of A. Okay, if you think like that, then the range and this column space you can correlate. Range is nothing but the column space of this matrix A. For this transformation, t of x equal to ax. Okay. Now we are going to the first example of linear transformation. Let V be the vector space of all real valued functions f defined on interval AB. That means V be the vector space of all real valued functions f defined on interval AB. Interval AB, suppose this is my interval AB. Interval AB, for example, let it be 1, 2, 1, 2. Which means that a straight line you draw, then this is 1 and this is 2. This is 2, and closed interval 1, 2 means like this. 2 points joining the set of all points in this set of all points between 1 and 2. Now then only there are infinite number of such functions exist between 1 and 2. For example, here I have joined 1 and 2 by a straight line. Now I'm going to join like this. Yes, this is a function f1. This is again a function f0, you can say. Now I'm going to define another function on this, like this. This is f2. So you can define infinite number of functions between 1 and 2, right? So similarly, we have in general the author has taken a b interval. So and the author is saying that V be the vector space of all such real valued functions f defined on interval AB. That means f1, f2 that we have already discussed, f0 we have discussed, f1, f2, f3, such like that. So these are the vector space. The author has defined, giving you the vector space as like this. Real valued functions f defined on interval AB with the property that they are differentiable. Okay, they are differentiable and their derivatives are continuous function on AB. That means they are differentiable means, let me yes, they are differentiable means what? This I'm taking this function f1. Okay, whether it is differentiable or not. Differentiable means it slopes. Okay, slope. So at each and every point of this function, which is defined under closed interval 1 2 having slope, a definite slope, right? So it is differentiable. Okay, differentiable in this interval 1 2. So that is what we mean by differentiable and continuous. Okay, so yeah, property. Okay, the property that they are differentiable and their derivatives are continuous functions on AB. So you understood that point. Then let W be the vector space. W again, the author defined W. First author defined B vector space, that is domain, and then defined the range vector space, that is W. Okay, vector space C of closed interval AB of all continuous functions on AB. Okay, and let D is the let D is the function from V to W, linear transformation from V to W. Be the transformation that changes F in V. Okay, V is there, W is there, and F is an arbitrary function F in V into derivative F dash, in F dash. Okay, this is what is transformation D from V to W means this. So, and in calculus, two simple differential rules we have. So let me examine whether the linear transformation or not. That is my problem. So for linear transformation of u plus v equal to t of u plus t of v, and t of cu equal to c into t of u, where c is an arbitrary and t is a scalar. So I'm taking f and g which belongs to v. Now I'm applying or acting my transformation on this fg, and I get d of f plus g. I get that is equal to the d. The transformation is defined as the derivative of f. Okay, f, derivative of f. Then d of f plus g. We have studied in our calculus class, d by dx of f plus g, where f and g are functions of x, equal to df by dx plus dg by dx. So we get d of f plus d of g, right? So the first axiom is satisfied. Now the second axiom is d of cf I'm taking is equal to, we know in our calculus class, we know that d by dx of a constant c into some x square, that is function of x square, that means c you can take it out, and c into d by dx of x square, that's equal to c into 2x. That is c. Yes, and x raised to n minus. That's the our property of calculus. So I am applying this calculus property here. Then I have c, d of cf is equal to c into d of f. So the two axioms are satisfied. So that is, d is a linear transformation. And it can be shown that the kernel of d is the set of constant functions on AB. that means I have to find out what is the kernel of this transformation D. So by definition, I have kernel means theta for x, so that theta for x, okay, theta for x, so that t of x equal to 0. Here the transformation is derivative. So derivative of a function is 0 means that function must be a constant function. So that means f of x equal to a constant c, like this, right? So you can, yes, f of x equal to 0, f dash x equal to 0, f of x equal to c, or f of x equal to c, f dash x equal to 0. Now, yes, that means f dash x equal to 0 means slope is 0. That means set of all x such that its slope is 0. Set of all function such that its slope is 0. That means if this straight line, for example, this is A, right, and this is B. So a straight line like this, straight line. It is a function f naught. So this is a kernel, kernel, uh, kernel of D, kernel of D. So that is the range, is kernel of the transformation. Okay. Moving on to the next topic, linear independent sets and bases. Linear independency of vectors. Okay, linear independent sets and bases. Consider indexed set of vectors, set v1, v2, v3, v4, etc., vp in a vector space V. And this set of vectors, indexed set of vectors in V, is said to be linearly independent vectors if the vector equation c1 v1 plus c2 v2 plus etc. cp vp equal to 0 has only the trivial solution, which means has only the zero solution, c1 equal to 0, c2 equal to 0, etc. cp equal to 0, its solution. So that is what the definition of linear independent vectors. Linear independent vectors. That means you cannot have a linear combination of these or these vectors. That is the concept. For example, let me consider this xyz coordinate that belongs to R3. So a point in this three-dimensional space, this is P, let it be P, then yes, R, yes, T is ordered triplet. Now a position vector drawn from origin O to this point P as OP is a vector. Let it be P. So this set containing this P alone is an example for linearly independent vector. Now let me consider a point at the origin O. That is O vector will be 0, 0, 0. That is nothing but our 0 vector in R3. So this 0 vector 0 and this P, when I consider the set of these two vectors, then you can say this 0 is linearly dependent on P. You can say it like this. This is an example for linear dependent vectors O and P. are linearly dependent. How O and P is, how can you prove that O and P are linearly dependent? Because C1, some scalar C into P equal to O. C, where C is equal to 0, belongs to R, set of ordinary numbers. So 0 into P, that's equal to O. 0, that means 0, that's equal to O. That means that you can have this linear combination CP equal to O, where this linear combination have only trivial solution, that is C is equal to 0, C is equal to 0. Okay, and so we have this is like CP plus D. Let me take D, DO equal to 0, where, and this equation, this is a linear combination of P and O, and this equation is having C comma D. The solutions of this equation is C comma D equal to 0. That means trivial solution. So as per the definition we have, as per the definition, we have the vectors 0 vector as well as P vector in R3 is linearly independent. Okay, now the set V1, similarly I am going to define the linear dependent, which will be exactly opposite definition. So the set V1, V2, V3, etc. Vp is said to be linearly dependent if one has non-trivial solution. Non-trivial solution means non-zero solution. Non-zero solution. Non-trivial means non-zero solution. That is, if there are some weights C1, C2, C3, etc., Cp not all zero, such that one holds, okay, this holds. In such a case, one is called a linear dependent relation among V1, V2, V3, etc. Vp. Linear dependency. Linearly dependent vectors we will say. Other is linear independent vectors. Okay. Now I'm going to take some example as well as some points. Here, this point in this textbook, that is saying that just as in Rn, a set containing single vector V, is linearly independent if and only if V not equal to 0. And also a set of two vectors is linearly dependent if and only if one of the vectors is a multiple of the other. That means, for example, I have P vector like this, and I have multiplied this P vector with 3, real number 3, or minus 1, then minus P we will get. Minus P means somewhere exactly opposite to this point, right? So this point is minus P, or 3P means 3 times, this is 3P. So these vectors are linearly dependent vectors. That is what this is saying. Vectors linearly dependent if and only if one of the vector vector is a multiple of the other. Okay. And any set containing a zero vector is linearly dependent, because zero can be expressed by coefficients, by putting coefficients equal to 0. So zero vector is linearly dependent always. And this point, if linearly independent, means V not equal to 0. A set containing a single vector V is said to be linearly independent if and only if V not equal to 0. That also you can imagine. Now, so in order to prove something, some vectors in R1, R2 or R3 or in general Rn, the vectors are independent or linearly independent or dependent. You have to prove that. Then what you have to do is you have to make these, you have to take these vectors and put as first column of a matrix A equal to, then you put the other vector and as the second column, then third, then fourth, and so on. Okay, m by n matrix of and the number of rows equal to number of entries in a vector. That means it belongs to Rn. So you can do it in and you have to solve this ax a into x equal to 0. You solve for x so that you will get some solution, and you examine that solution, you analyze that solution, whether it is all the solutions are 0, that means trivial solution, or it is having a non-trivial solution or unique solution, like that. And you will decide whether the vectors, that is vectors which are the columns of the matrix A are linearly dependent or independent. You will conclude that also. Then now if our vectors under consideration is not belongs to Rn, it is some polynomial functions or like that, some polynomial functions or some sine or cosine functions, then you cannot put it as the columns of a matrix A. Then what? But you have to identify whether those vectors are dependent vectors or independent vectors. So in that situation, how we do is we will going to define a theorem. We will give a theorem like this. Theorem is an index set of vectors v1, v2, v3, etc., vp of two or more vectors with v1 not equal to 0. 0 means 0 vector is linearly dependent. Is linearly dependent if and only if some vj with j greater than 1. That is it can be v2, v3, v4, etc., vp. So some vj is a linear combination of the preceding vectors v1, etc., vj minus 1. That means some vector vj, let us take it as v2 will be is equal to some linear combinations of v1 plus c2 c3 v3 plus c4 v4, etc. So this is Vj minus up to Vj minus 1. That means Vj minus 1 means V2. J is equal to 2. So 2. So 2 minus 1 V1. So C1 V1 only you get this. So V2 equal to C1 V1. Then the yes, this vector V2 is dependent vector on V1. Okay, that means V1 vector you have, then V1 vector you scale it. Scaling is the operation, so scale is you will get V2. So V2 is dependent on V1. So that is the theorem. So you can apply this theorem whenever the vectors are like V1, V2, V3, etc. Vp vectors are not belongs to Rn in general. Rn. Okay, now we will discuss some examples. Now I am going to apply the theorem 4 so that I can solve one of the example problem like this. Yes, this is my problem. That is, I have defined three vectors: p1t equal to 1, p2t equal to t, p3t equal to 4 minus t. So then we have the vectors that p1, p2, p3 is linearly dependent in P, polynomial P. That means P is the set of all. P is the we have proved that in our previous class. P is the set of all polynomials. That is again a vector space. So it is in. So this P1, P2, P3 belongs to P. So dependent. So you have to prove that, or you have to understand. You have to what? Yes, you have to. You should know that this is a linearly dependent set in P. So how to prove? How to prove means you have to apply this theorem number 4. That is an indexed set V1 set V1, V2, V3, etc. Vp of two or more vectors with v1 not equal to 0 is linearly dependent if and only if some vj with j greater than 1 is a linear combination of the preceding vectors v1 etc. vj minus 1. So we apply here. That means I have p3 of t, that is 4 minus t, and p2 of t, p1 of t 1. So you just p2 of yes, you p1 of t minus p2 of t, you will get 1 minus t, or that is not equal to p3 of t. So then I have to make this as 4. So for p1, so for p1 minus p2 of t, I will get 4 minus t. So I will get this p3 of t. So this, that means the p3 okay, in which j is equal to 3, j equal to 3 and j equal to 3, and this set p1 is not equal to 0. So these conditions are satisfied. So p3 equal to is equal to a linear combination of p1 and p2. If this is happening, then you can say it is they are linearly dependent. So it can happen. It can happen like this. You can like this relation. So by theorem 4, p1, p2, p3 are linearly dependent. So that is our example problem. Now let us take up the second example. This example, yes, example 2. That is the set we have the vector sin t vector and cos t. These are two functions, right? That these functions are considered to be vectors, two vectors. So these vectors, the set of these two vectors is linearly independent in C closed interval 0, 1. Let me check this. Let us check it out. So Okay, this is our sine t. Okay, and only taking, yes, this is sine t and this is cos t. So my sine t and cos t only defined between 0 and 1. 0 and 1, like this. This is my only this portion up to this. Here 1 0, this portion, right? This portion up to this only. So this portion only we have defined it. So sine t cos t, if there is, that these are two independent functions, because we cannot express this sine t equal to some constant c or some real value c into cos t. This is impossible. So we cannot represent it as a linear combination. As well as cos t also. Cos t is not equal to some real value, some arbitrary value into sine t. So that is not possible. But sine uh, t sine pi by 2 minus t is equal to cos t. That we know, right? That we know. But this is not linear. This is not linear. So these are two independent vectors. Because yes, the space of all continuous functions on 0 less than or equal to t less than or equal to 1, because sine t and cos t are not multiples of one another as vector in C01. There is no scalar C such that cos t equal to C sine t for all t in 01. Okay, that means if you are observing the two graphical representations, this is rising from 0 to 1, this is falling from 1 to 0. So these are exactly opposite values you cannot generate from one another. Okay. Cos t are not okay. However, sin t cos t, set sin t cos t and sin 2t is linearly dependent because of the identity sin 2t equal to 2 sin t cos t for all t. Right? This is our example. Hope you understood. Now